Hello again, this is Dr. Armand bringing you another exciting lecture in General Chemistry 1 laboratories. In this lecture, we'll be discussing Lab 2, which is involving density. This is the first lecture that you will be using the Haiti McNeil virtual labs. That's where you'll complete the lab for this density lab. So sit back, relax, and enjoy the show. So this is Lab 2, dealing with density. So in this lab, we can expect to determine the density of solids, determine the density of liquids, and how do we do that? Well, we measure two things, the mass and the volume. Before we get into the actual calculations, let's talk about a little bit about what density is. And so density is a property of a substance. And with matter, you have properties that describe a characteristic of a substance, and you have changes, which is an action undergone on a substance. And there are two categories of properties slash changes. These are chemical and physical. We'll start with chemical first. Chemical changes or properties are a change or property that changes the identity of the substance. So what you start with is not what you end with. For example, when a metal rusts, it's a chemical change. Or when sodium is oxidized by water, that is a chemical change because the resulting substance is not what you started with. Likewise, when you digest food, it's a chemical change because the food going in is not the same as what's coming out. A scab forming over a cut is a chemical change. A leaf changing color is a chemical change. You can't go back to what you started with. It's something new. And so properties that describe a characteristic of a substance where it changes its identity is a chemical property. For example, ethanol is flammable. That's a chemical property. Sodium is an oxidizer. That's a chemical property. So those are chemical properties and changes. Now we also have physical properties and changes, and these don't alter the composition of the substance. It just changes its A, physical state, or B, appearance. And so just like chemical changes, physical changes is some type of action on a substance. So for example, excuse me, dissolving salt in water is a physical change. You're not changing the identity of salt or water. Brewing coffee is a physical change. You're not changing the identity of coffee. Melting ice is a physical change. You're not changing the identity of what ice is made up of. Now, physical properties describe characteristics that don't change the identity. For example, the melting point of uh, the melting point of ice is 0 degrees Celsius. That's a physical property. The boiling point of ethanol is 78.6 or 78 degrees Celsius. That's a physical property. Copper is a reddish orange color. That's a physical property. Um, the density of lead is a physical property. It doesn't change the identity of the substance. So now we're going to look a little bit more into physical properties and chemical properties. These can actually be categorized into different types. And this goes for both chemical and physical, but we're mainly just going to focus on the physical ones for the next part. And these are just examples of physical and chemical properties. So for example, when you freeze water, which is shown in the top left-hand corner, when you freeze water, this is a physical change. You're not changing the identity of water. When you combust hydrogen and oxygen to make water, this is a chemical change. Because if you notice on the product side, we have a different material than on the reactant side, and we can't go back to it by physical means. When water is reacted to form hydrogen peroxide, this is a chemical change. You can't go back to what you start with. The formation of frost is a physical change. You're going from one state of water to another state of water. These are just some examples of chemical and physical changes. Now, with physical properties and chemical properties, but we'll just focus on physical, there are two categories of these properties. So one is extensive physical and chemical properties, and this depends on the amount of matter present. The most common ones are volume and mass. A less common one is called heat capacity. So the more volume you have of a substance, the more matter you're going to have. The more mass you have of a substance, the more matter you're going to have. So those depend on the amount of matter present. The other class is intensive physical properties, which does not depend on the amount of matter present. So it doesn't matter how much of this material you have, it won't affect the property. And these are things like boiling point, melting point, density, color, malleability, ductility, what else? Solubility. So these don't depend on the amount of matter present. And these are called intensive physical properties. So 1 pound of water boils at 100 degrees Celsius. The same as if you had 1 ton of water, it's still going to boil at 100 degrees Celsius. Because again, boiling point is a intensive physical property. It's not going to depend on the amount of matter. So whether you have 1 pound of water or a ton of water, it's still going to boil at the same temperature. So for example, what weighs more, a pound of feathers or a pound of lead? So we have 2 bags. One contains a pound of feathers, one contains a pound of lead. Which one would weigh more? And the answer to that question is they both will weigh the same because they're both 1 pound of each. Now, since the density of feathers is less than the density of lead, it would take more feathers to make 1 pound. Whereas for lead, it would take less lead to make 1 pound. But they both weigh 1 pound. And feathers has its own unique density, and lead has its own unique density. It doesn't matter how much lead you have, the density is always going to be the same. Just like with feathers, it doesn't matter how many feathers you have, the density of the feathers is still going to be the same. So now let's focus a little bit more on density. So density is the ratio, not the ration. My bad, typo there. It's the ratio between the mass and volume of a substance. So density is just taking the mass of a substance divided by its volume. The SI unit, which is the standard international system of units for density, is kilogram per meter cubed. And that's because kilogram is the SI unit for mass. And meter cubed is the SI unit for volume. And that's why, since density is mass over volume, the SI unit is kilogram per meter cubed. However, that is not the common unit. The common units are grams per milliliter for solids and liquids, or gram per liter for gases. And one thing to remember is that 1 milliliter equals 1 centimeter cubed. Now, density is a unique property because we can use it to distinguish between two or more substances, because every substance has its own unique density associated with it. And for most substances, the solid is the most dense, followed by the liquid form, followed by the gas form. However, we should know of one common exception, which is water. And for water, the solid is less dense than the liquid. And that's why if you have a cup of water, the ice floats on the water because ice is less dense than water. Now, if you increase the mass of your sample at constant volume, you're going to increase the density. If you increase the volume at constant mass, you're going to decrease the density. So a graphical way of determining the density of a substance is to plot the mass versus the volume of a substance. And so when you graph the mass of a substance versus its volume, the slope equals the density. So in this graph here, we have mass on the y-axis and we have volume on the x-axis. And so as we plot the mass and volume of component A, we generate a linear line. So if you were to determine the slope of this line, that would tell you the density of A. Likewise, when we plot the mass and volume of substance B, when we plot the data, we'll be able to get a linear regression, and the slope of that line would tell us the density of B. Now, since A has a steeper slope than B, that tells you the density of A is greater than the density of B. So again, since A has a steeper slope than B, A would have a greater density than B. And so this is one way you can determine the density by plotting the mass versus the volume of a substance. Perform linear regression on the data. The slope of that will tell you the density. Again, the steeper the slope, the greater the density is. So one thing we want to touch on before we talk about calculations is significant figures in measurements. So when we're taking measurements, how many digits are significant? And significant figures in measurements are the number of certain digits plus one uncertain digit, or what we refer to as an estimated digit. Now, these certain digits are dictated by the smallest tick mark on the measuring device. So for this graduated cylinder, the certain digits would go to the 1 place. So the 1's place, we know for certain what the volume is because it's the smallest tick mark. The smallest tick mark represents 1 milliliter, which means we know for certain that we would know the volume. Now the estimated digit is typically the placeholder to the right of the last certain digit. So the estimated digit here would be in the 10th place. And this is for this 50 mil graduated cylinder. Now, when you're reading a liquid, when you're measuring liquid in a piece of volumetric glassware, you have to measure it at the minimum of the curved surface, which is called a meniscus. So you would read at eye level what the value of the liquid is at this part of the curved surface. That way you get an accurate reading. So you have to be eye level with the meniscus. That curved surface is referred to as a meniscus. So now if we look at this measurement, we know for certain it's 43 milliliters because the smallest tick mark is 1 milliliter, so we know for certain it's 43. Since the smallest increment is 1 milliliter, that's the most, I guess you say, precise the certain digits can be. So the uncertain digit would be in the tenths place. And typically, for the uncertain digit is either usually a 0 if it's close to the smallest tick mark, or it's a 5 if it's in between, typically. But anything would be valid. You could use between, say, 0 and 5. But since the smallest increment is 1 milliliter, the estimated digit would be in the tenths place. So we're either going to put a 0 or a 5. And so here, since it's close to 0, we say 43.0 milliliters. This has 3 significant figures. Now let's look at these rulers. So we have 2 types of rulers. These are in centimeters, by the way. For standard measurements, it's a little bit different. So you always want to try to measure in the metric units. So these are both, again, centimeters, just 2 different types of rulers. So for ruler A, our certain digit, the smallest tick mark, is in the ones place. So we know for certain it's 4 centimeters. Now we have to estimate the next placeholder, which is the tenths place. So we're going to see if it's close to 4, we would put 4.0. If it's between, we would put, for example, 4.5. Now, anything would have been valid. So if you put 4.6 or 4.7 or 4.8, that's also acceptable. The fact is that this only has 2 significant figures. Now, if we look at ruler B, we know for certain that it is 4.8 because the smallest increment is 0.1 centimeters. So our uncertain digit is going to be in the hundredth place. And typically, and this is a typo here, typically it's going to be either a 0 or a 5. So based on where it's at, we would call this 4.85 centimeters. So you could have put 4.85, 4.84, 4.86, 4.87. The fact is that you have to have 3 significant figures. So notice here that the smaller the smallest increment is, the more precise your measurement becomes. So here we have another graduated cylinder. Again, we read the volume at the bottom of the meniscus. So we know for certain that it is 50, 51, 52. So we know for certain it's 52. So if we think it's close to 53, we would say 53.0. If we say, well, it's between 52 and 53, we would say 52.5. So here, since it's very close to 53, we would record the measurement as 53.0 milliliters. Again, this has 3 significant figures. So you have to include the certain digits and one uncertain digit. So here we want to know how long this metal strip is in centimeters with the correct number of significant figures. So we know for certain it's 7.2 because the smallest increment is 0.1 centimeters. And so to do the uncertain digit, we have to go to the placeholder to the right of the smallest certain digit. So since tenths is the smallest certain digit, hundredths would be the estimated digit. And so if you think it's between 0.2 and 0.3, you would put 7.25. If it's on 0.2, you would say 7.20. But you could also put 7.24, 7.26, 7.27. It's just an estimated digit. The common practice is either to do a 0 or a 5 for the estimated digit. Here we have 2 thermometers. So on the first one, smallest increment is 1 degree Celsius. So our certain digits is 21. Estimated digit would be the tenths place. So we would estimate, for example, 0.5. So our measurement would be 21.5 degrees Celsius. This has 3 significant figures. Now if we look on the right side, our smallest increment is 0.1 degrees Celsius. So our certain digits is 21.12345 21.6. Our estimated digit, hundredths place. And so we can estimate, usually it's a 0 or a 5, so I'm going to estimate 0.05. And so our measurement is 21.65 degrees Celsius. So this has 4 significant figures. So the more precise your measuring device, the more significant figures you would have in your measurement. Also acceptable would have been 21.66, 21.64, 21.67, etc. So how do we calculate density? Well, for density, you need to measure the mass and the volume. And so for the mass, we typically use an electronic balance. And for anything electronic, every digit shown is significant. So for electronic devices, all digits shown are significant. So whatever is displayed on the screen for an electronic device, everything is significant. So in this diagram to the right, this balance would have, this measurement would be 125.30 grams, which would have 4 significant figures. And so typically we measure in grams for density because for solids and liquids, the common unit is grams per milliliter. Now for measuring the volume of your substance, if it's a liquid, typically we use a graduated cylinder. Again, you have to measure at the minimum of the curved surface, which is referred to as the meniscus. Now for a solid, it depends. So for the solid, if it's a regular shaped object, we can do volume by calculation. So for example, if it's a sphere, we know that the volume of a sphere is 4/3 pi r cubed. If it's a cube, we know the volume of a cube is just the side of the cube squared. If it's a cylinder, we know that the volume of a cylinder is pi r squared h. So if it's a regular shaped object, you can measure and determine the volume through calculation. Now, if it's an irregular shaped object, we have to use volume displacement. So what we do is we have a graduated cylinder. It's filled with a certain amount of water. We add our object. The volume of the water increases. The difference in the final and initial volume is the volume of the object. Now you have to make sure that whenever you're performing volume displacement, that you don't use a substance that is soluble in water. Then it will not work. But this is a common technique to use when you have an irregular shaped object. So here we want to calculate the density of this spherical object shown below. So we're going to do volume by calculation. Oh, and I forgot to put the mass here. So let me put the mass. So the mass is, we'll say it's 7.75, well, not 7. Let's say it's 3.35 ounces. What is the density of the object in grams per milliliter? So for the density, we need the mass and we need the volume. Well, the mass we can determine because we know it's 3.35 ounces. We can multiply this and convert it to grams. We know 1 pound is 16 ounces. So we divide by 16. And then we know that there's 453.6 grams in 1 pound. Let's do that again. So 3.35 ounces, we divide by 16 because there's 16 ounces in a pound, and then we multiply by 453.6 grams in 1 pound. And we get 94.973 grams. That's the mass. Now for the volume, since this is a sphere, we know the volume equals 4/3 pi r cubed. So we need to determine R in order to calculate the volume. So what is R? R we don't know. But from the measurement, we know that the diameter of the sphere is 5.7 centimeters. So if we know the diameter, we can determine the radius, which is 5.7 divided by 2. 2.85 centimeters. So now we can determine the volume And we get the volume to be 96.97 centimeters cubed. Now remember that 1 centimeter cubed equals 1 milliliter. So now we can calculate the density, which is going to be 94.973 grams divided by 96.97 centimeters cubed. And we get 0.9794. Now we got to round to the correct number of significant figures. So we look at our original numbers. Our mass had 3 significant figures. Our density was 2, so this should be rounded to 2 significant figures. So it'll be 0.98 grams per milliliter. That's volume by calculation. Oops, well, I had 6.27. I used a different mass, but you see we still got the same volume. So again, it's rounded to 2 sig figs because the diameter only had 2 sig figs. Now we have a density of a solid by volume. So volume by volume displacement method. So we have a ring that's 3.85 ounces. Volume displacement was used to determine the volume of the ring, shown below. Calculate the density of the ring in grams per milliliter. So we know density is mass over volume. We know the mass is 3.85 ounces. It's given to us in the problem. So we're going to convert the ounces into grams. And I don't think that's a typo there. Yeah, so this should be, and I'll correct these in the PowerPoint and then repost the PowerPoint as well. So this should be 3.85. Or is it 1.35? Yeah, my bad. So the mass is actually, and I'll fix this and repost the PowerPoint, should be 1.35 ounces. So this is also 1.35 ounces. Now that we determined the mass in grams, V final minus V initial gives us the volume of the object. So the ring here has a volume of 4 milliliters. So therefore, since the volume has 2 sig figs and our mass had 3, our answer should be 2 significant figures, so 9.6 grams per milliliter. So that's the density of the ring. And again, I'll go back in the PowerPoint. Hopefully by the time you see this, it's corrected. It says 1.35 here. This is how you do calculation, do density by volume displacement. So just to kind of some pointers on how you should do, what your to-do list for this experiment. Make sure you read over the lab lecture notes, watch the lab lecture video. Also, maybe review over these concepts in your textbook. This is chapter 1 material. In addition to reading all those items, make sure you go to the Hayden McNeil site and read over the background information for the density lab. So once you do all that reading, Then go and complete the density calculation assignment on Blackboard. Then complete the lab lecture quiz for density on Blackboard. So again, both of these are on Blackboard. And then once you do all of this, then you go to Hayden McNeil's site and complete the virtual lab on density. And so what you'll do is you'll click on the book, it'll take you to the experimental information, and then there's a blue square you click on to start the experiment. So as you read the information, you complete the experiment. Make sure you take notes of your observations and measurements. Okay. Once you complete the virtual lab, do all the virtual lab questions on the Hayden McNeil site. Then you go and complete the post-lab assignment on Blackboard. And so this is what you should be working on for Lab 2. So that concludes the video lecture on Lab 2, which is density. This will be your first Hayden McNeil virtual lab. So I hope you enjoyed the video. If you learned something new or liked listening and watching it, please click the like button. And on that note, Dr. Armand signing off. Until next time.